nice introduction. So, in continuation with my previous lectures, so this will be today's talk will be the final talk for a series of lectures which I gave during my stay in this campus. So, in my previous lectures, I discussed basic results related to non-linear spaces and Banach spaces, and then I also gave a series of examples. In continuation of that, there are other examples, you see, and then examples of non-linear spaces, which on Banach spaces. So you take a let V. Oh, sorry, there is a duster here. Duster, okay. I think all of you know what inner product space is. That V, this is be an inner product space, be an inner product space. Product space. Then if you define for each x belonging to V, define this norm of x. This is a function, so it is nothing but inner product of x with itself, and take the square root, because inner product of x with itself is always greater than equal to 0. So this is 0 if and only if x is 0. So these are basic, using the basic properties of this. Then if you define like this, then this V is, this is again a norm linear space. Is a normed linear space. This is a non-linear space. Now, if V is finite dimensional, if V is not, so this is a non-linear space. If this is finite dimensional, then this becomes a Banach space. Every finite dimensional non-linear space is a Banach space. So if you take any finite dimensional inner product space, it can be realized as a Banach space. And there is a special category of Banach spaces which come from where norm is induced by the inner product. This is here, this norm is coming from induced by, we call it induced by inner product. And such, so this is a Banach space, and if norm is induced by, since this norm is induced by inner product, and these are such norm linear spaces where norm is induced by inner product. You call them Hilbert space. They are first introduced by famous German mathematician called Hilbert. So they are called where, since this V with this is called a Hilbert space. So norm is induced. This V. Now, if norm is here, norm is induced by inner product, and if it is Banach space, if this V with this is where this is a norm, this norm is induced by inner product, then you call it where norm is induced by inner product, and this is called a Hilbert space. So, for example, if you take V is equal to Rn or Cn, then you have this. Then for x is equal to xi, I is equal to 1 to n, y is equal to yi, I is equal to 1 to n. So, if you define this this x comma y is nothing but summation xi yi conjugate, I is equal to 1 to n. Then this is inner product, and this, then one can verify that this is inner product. This is inner product on this V, and therefore now if you take this norm induced by inner product, what will you get it? this is nothing but summation xi bar, xi bar, and I is equal to 1 to n, and then whole to the power 1 by 2. So this is nothing but summation mod of xi square, I is equal to 1 to n, and whole to the power 1 by 2. And this is nothing but the 2 norm, p is equal to 2. This gives you the p is equal to 2. So if you take v is equal to Rn or Cn, so this, therefore this H, this is a Hilbert space, Rn or Cn with 2 norm, because this 2 norm comes is a Hilbert space. But these are all examples of finite dimensional Hilbert space. So if you take Rn or Cn and you look at 2 norm, p is equal to 2, then they are special class of Banach spaces, and we call them Hilbert spaces. And Hilbert spaces are, we will see why these Hilbert spaces are important, but there could be infinite dimensional Hilbert space also. So I will define, now I come to this major theory. So LP space of mu. So how do you define? Let definition, let X be mu be a major space. All of you, I hope you know major spaces. So what is a major space? It is a triplet. This is X is a non-empty set, and this B is a sigma algebra on X. This is a sigma algebra. By sigma algebra, what is sigma algebra? Sigma algebra, a collection of, so this is a non-empty set, a collection of subsets of X, a non-empty collection, suppose this is a non-empty collection of subsets of X. X is called, so suppose non-empty collection, script B, we are denoting by script B, is called a sigma algebra on X if, number 1, so it is elements of this collection are subsets of X. Number 1, if A belongs to script B implies A complement also belongs to script B. That is, it is closed under complementation. And number 2, if An is any sequence, suppose you have a sequence of elements. If N is any sequence in this sigma algebra, in this collection of subsets, then union of N, this also belongs to this collection. That is, it is closed. So this first property is what we call as B is closed under complementation. And number 2 is closed. This B is closed under countable union. So we call it is closed under countable union. So a non-empty collection of subsets of X is said to be a sigma algebra, then if it is closed under complementation and also closed under countable union. So now one remark here. So first thing is, so I think so many of you do not know what sigma algebra, and so I am giving a cursory introduction, a brief introduction of what major space means. So you look at, so every sigma algebra, if B is a sigma algebra on X, then this empty set and whole set, they are always contained in this sigma algebra. So I can show that. Why? Because it is a non-empty collection. So if you look at this, so there is at least one element, number 1. Suppose A belongs to this. Now, at least one element, because this is non-empty. Then what do we got? A complement would also belongs to this. And it is closed under countable union. Therefore, it is also closed under finite union. So A intersect A union A complement. This also belongs to this. And what is A this implies X belongs to this sigma algebra, this collection. Now second is, so X belongs to this, and therefore empty set is the complement of, so this implies X complement, which is empty set, this also belongs to me. So the minimum number of elements a sigma algebra has are 2 elements on any non-empty set, and this is a sigma algebra. By the way, if you take this B0, this empty set and the whole set is a sigma algebra. Therefore, on any non-empty set, there is a smallest sigma algebra. And what is the largest sigma algebra? Power set of X. So in between there are many sigma algebras, and the largest sigma algebra is, suppose I write this B1 and this is power set of it. So on any set there are at least 2 sigma algebras, namely containing just 2 elements, and the other one is whole power set of X, which contains every subset of X. However, there could be many. So now, second point. And given a sigma algebra, what is a measure? So measure, this is a sigma algebra. By a measure, it is a function from this sigma algebra to 0 to infinity, non-negative real valued function, extended real valued function, non-negative. So a measure mu is a function. It is a function whose domain is a sigma algebra. This sigma algebra such that number 1, mu of empty set is 0. So for empty set as measure 0, this notion of measure came out of the notion of length, area, and its generalization gave rise to measure. And the first such measure is what we call the Henry-Lebesgue. Henry-Lebesgue introduced this notion of what we call a Lebesgue measure. Number 2, if N is any collection of elements pairwise disjoint, any countable collection, because this is countable collection of pairwise disjoint elements in this sigma algebra, then this mu of this union of A, because they are pairwise disjoint, so measure of this must be equal to, it is the sum of mu of. Just like you have a duster, you want to measure its length. Suppose you divide into parts and take the length of each of them and sum, you will get the length of this original this duster. So that's the idea. So you are extending it to countable sets. And the example of, one simple example of measure is, suppose you take X to be set of natural numbers and you take the sigma algebra to the power set of X. Power set of X. X is natural numbers, example. And now, so for each subset A of X, so mu of A is nothing but this cardinality, number of elements in A. This cardinality of A. Cardinality of A. So it could be either finite or infinite. You see, cardinality, this cardinal number of A is finite, and if A has any elements, otherwise it is infinite. So then this mu is a measure. This is a measure, and this measure has a special name. Mu is called the counting measure. It counts the number of elements. Called the counting measure. The another example is, those who are in PhD or MSc final, they would know. You take X is equal to set of real numbers, and V is the sigma algebra of all Lebesgue measurable sets. Lebesgue measurable sets, and mu is the Lebesgue measure. Lebesgue measure. So Lebesgue measure is generalization of the length for the intervals. So then this X, the mu, be a measure space. Measure space. There is another example. Suppose I write like this. Suppose your X is nothing but any non-empty set. Suppose I write this B is equal to empty set and the whole set. Now I define a function mu from B to 0 to infinity as mu of empty set is 0 for any. So there are only 2 elements. Mu of empty set is 0, and mu of x is equal to 1. Suppose I write this. This is if mu of empty set is 0 and mu of x is equal to, or you can take infinity. See? So mu of empty set is 0 and mu of x is infinity. This is also a measure. Or you can take any finite non-negative number. So this also is mu is a measure. So this way, and the class of measurable sets are elements of this sigma algebra. So given a sigma algebra and x comma b, this ordered pair x comma b is called a measurable space. So this is a measurable space and this is called measure space. Measure space is a triplet where x is first element, first component of this triplet is a non-empty set, b is a sigma algebra on x and mu is a measure on measure whose domain is this sigma algebra, which satisfy these two conditions. Mu of empty set is 0 and mu is countably additive. This property we will call mu is countably additive. So I was giving the definition of LP space. So in that process, I explained this what we call as measure space, because when I had this understanding, I had this premonition that some of you don't know what measure space is all about. Therefore, I gave this definition. So now, what is LP space of a measure space? So when you have a measure space, you can define measurable functions. So in general, measurable function. So what is a measurable function? Suppose f from x to r union plus minus infinity. Extended real valued function is called a measurable function. It is called a measurable function. What? If for each real number alpha belonging to R, this set all x belonging to x, fx greater than alpha, that is, you can write this as f inverse of minus infinity. So alpha to infinity. This is nothing but all x belonging to x such that fx greater than alpha. This is a measurable set. So that means this belongs to the sigma algebra. So you have a measure space. So for each alpha belonging to R, this f inverse of alpha to infinity is a measurable set. Then you call it, this real valued function is measurable, and a complex valued function is measurable if its real and imaginary part are both measurable functions. Real and imaginary part of a complex valued function is they are real functions. So if you have complex valued functions, you extend this definition for complex valued measurable function. Now I can define LP space with this understanding. See, in measure theoretic terms, so number 3, 2 point, let f and g be two measurable functions. Then you say that f is equal to g almost everywhere with respect to mu if all x belonging to x, the points where f and g do not agree, fx is not equal to gx. This measure of this must be, this is a measurable set, mu of this must be 0. Then we say that f and g are equal almost everywhere. So, for example, if you look at, suppose your x is equal to interval 0, 1, and then then you look at this function, and b is the sigma algebra of all Lebesgue measurable subsets of x, and mu is the Lebesgue measure, which is restricted on this Lebesgue measure. Now, if you look at this function, f and g are, so I give two functions. So if f and g are equal, they are equally almost everywhere. Because if f and g are equal, then fx is equal to gx for all x belonging to x. So that means all x belonging to x, fx not equal to 0x, this will be empty set. Empty set has measure 0. So therefore, if f is equal to g, if f is equal to g, then f is equal to g almost everywhere. But converse is not true. But converse is not true. So the example is here. Example. So you take x to be closed interval 0, 1. B is the sigma algebra of all measurable subsets of x. And look at this mu to be Lebesgue measure x restricted on this. Then now you look at this function. Suppose let f from x to r as f of x is equal to, so f of x is equal to, f of x is nothing but, suppose this is 1 when x belongs to q intersection x. Q means set of rationals, yeah, x is a rational number, so if x is rational and this is -1 if x is irrational. Okay, so suppose this is -1 and you take g of x and g, another function g from x to r, g of x is equal to, so it is constantly -1 for all x belonging to x. Then f is not equal to g, so whenever x is rational, fx is 1 and gx is -1, so f is not equal to g, right? But f is equal to g almost everywhere with respect to this measure, because, so if you look at all x belonging to x, fx not equal to gx. What is the measure of this? Lebesgue measure of this? This is nothing but mu of q intersection this x. Q is the set of rational numbers, all the rational numbers in this. So rational numbers are countable. Every countable set has Lebesgue measure 0. So therefore this set is also countable. So it's Lebesgue measure because you are taking this measure. Okay. So this means f is equal to g almost everywhere with respect. Okay. With these two ideas at the backdrop, I can define LP space of a measure space. So given a measure space, LP of mu is nothing but all f from x to c complex valued functions. So f is measurable. So complex valued function is measurable means its real and imaginary part is measurable, and such that, and so if you take this integral of mod of f to the power p, so LP, so you can write this, so you can take 0 less than p less than infinity, right? This integral to the power p d mu over x, so its integration is less than. And you can also define L infinity, p is equal to infinity. So what is L infinity of nu? So it consists of all functions, equivalence class of functions x to c, such that essential supremum of mod of f, which is nothing but infimum of all m greater than 0, infimum of these numbers, such that mu of all x belonging to x, mod of fx greater than m, this has measure 0. So you look at all those numbers such that if your mod of fx is greater than m, this set has measure 0. So this is called essential supremum norm. Obviously this is greater than 0. Similarly this is greater than 0. Then now we define, so LP for 1 less than equal to p less than infinity, define norm of p norm. So it is nothing but, this is integral mod of f to the power p over x d mu, and then you take whole to the power 1. And for infinity, for p is equal to infinity, it is nothing but essential supremum of mod f. Then this LP of mu 1 less than equal to p less than equal to infinity with P norm. So LP of mu means with this P norm, where 1 is less than equal to, these are all Banach spaces. They are all Banach spaces. So given any major space, there is an underlying Banach space here, LP of mu. And one can show that this is a non-linear space. And to show that this is a Banach space requires a little bit, it has some complication. It needed this result. So theorem, a non-linear space, a normed linear space is a Banach space. X is a Banach space. It is a Banach space if and only every absolutely summable series is summable in X. What does this mean? Absolutely summable series. Suppose you have a non-linear space. What do you mean by absolutely summable series? Do you know an example of an absolutely summable series which is not summable? So example of absolutely summable series which is not summable. So what does it mean? So see, if you take the R with modulus. So a series of real numbers xn in R is, so modulus works as a norm here. You see, this modulus is a norm on the set of real numbers, so complex numbers. So this series is said to be, this series n is equal to 1 to infinity in R is called absolutely summable, absolutely convergent or absolutely summable. What does this mean? Summable if summation modulus of xn n is equal to 1 to infinity is less. This is finite. This sum of this series, take the modulus and look at this series, associated series. If this series is convergent, then you say that original series of real numbers is absolutely summable. So in the real numbers, if a series is absolutely summable, it is always summable. You know this. If a series is absolutely convergent, it is convergent. Converse is not true. So do you know such an example? Converse is not true. You look at this series. Suppose you look at minus 1 to the power n by n is equal to. So this is convergent. Leibniz theorem says that this is convergent series of real numbers. But if you look at this modulus, if you take modulus of 1 minus 1 to the power n by n, so what will be this? This is nothing, modulus is, this is 1 by n, this is divergent. So its sum is not finite, divergent. This is not convergent. But in a real number with this as modulus as norm, every absolutely summable series is summable. And therefore it is a Banach space. This theorem says that if you have a non-linear space, it is a Banach space if every absolutely summable series is summable. But if you have a non-linear space, what do you mean by absolutely summable series? Absolutely summable series. So that X, suppose you have a non-linear space, be a non-linear space. Non-linear space. A series in X, an infinite series xn in X. So each xn belongs to X. It's called absolutely summable if summation norm of xn. So instead of modulus, here it was norm. See, on R as a vector space, this modulus was the norm. So now you generalize this notion which is available here. So if this series, now this is a series of non-negative real numbers, because norm is always greater than equal to 0, is summable. If this series is summable, means convergent. Summable or convergent. then you call this series of in X is absolutely summable. So, so when we say that series is summable, infinite series is summable, you look at the nth partial sum, sequence of nth partial sum. If it converges, then you say that that series is summable. So if you take nth partial sum in X, it must be convergent sequence in X. Okay. So I can give example of a series which is not absolute. Suppose you take X is equal to L infinity, C00, and we take this infinity norm. So now let this xn is equal to, so you look at this nth place 1 by 2 to the power n, elsewhere all 0. So this belongs to C00. Now if you look at this series summation, so infinity norm of xn, what will be this series? Infinity norm, what will be infinity norm of this? This is summation 1 upon 2 to the power n. And this is convergent, is summable. Therefore this series, so that implies, this series summation xn is absolutely summable. But what is this? If you take the sum of this series xn, n is equal to 1 to n, what will be this? This is converging to 1 by 2 square, 1 by 2 to the power n, and it goes on. And this does not belong to C00 because each term is non-zero. So therefore, a sequence belongs to C00 if except for finitely many terms, all of them must be 0. But here it is the opposite. None of the terms is 0. So this does not belong to C0. So therefore this series is absolutely summable but not summable. And this implies this C00, the infinity norm, is not a Banach space. Okay. So this result, a non-linear space is a Banach space if and only if absolutely summable series is summable. Very important result. Using this result, we can show that this LP space. So LP space is a Banach space. So LP space, so this is a theorem which uses this LP of mu with P norm 1 less than equal to P less than equal to infinity is a Banach space. And it simply uses this result that you show that every absolutely summable. To show that this is a Banach space, you have to show that every absolutely summable series is summable. And this is very easy to see, and uses various convergence theorems like monotone convergence theorem, dominated convergence theorem, a lot of major theory, but I do not have time to prove this result, but you can rest assured that this is Banach space associated with any major space X, B. So every major space gives rise to a Banach space, a collection of Banach spaces, and they are mostly infinite dimensional. Okay. So, but now a special case is when suppose your X is n and this sigma algebra is power set of X and mu is the counting measure. Counting measure I have already defined. Counting measure. Then this LP of mu, then this capital LP of mu, this becomes little LP. This becomes little LP 1 less than equal to P less than equal to. So these are sequence spaces, and they are all Banach spaces, infinite dimensional Banach spaces. So little LP is a special case of this when X is n, B is the sigma power set of X, and mu is the counting measure. Then this converts into LP with P norm. P norm already I have defined. P norm. So what is LP here? LP, in other words, this LP, in other words, What do you get LP? This is all sequences because X is the set of natural numbers. So functions are all sequences. N is equal to 1 to infinity such that this integral of X, this integral of this over with respect to its measure mu. So this integration is replaced by mod of xn to the power p. N is equal to 1 to infinity and this is less than infinity. And for L infinity, so this is 1 less than equal to p less than infinity. And L infinity would be all these sequences such that xn n is equal to 1 to infinity, such that supremum of, they are bounded sequences, xn n greater than equal to 1 less than. The essential supremum of x will be this supremum of mod of x. And this supremum, so that means L infinity consists of all bounded sequences of complex numbers. And here LP for p less than infinity, it consists of all sequences of complex numbers satisfying this condition. So this is this general situation leads to a particularly simple situation when your x is n, mu is counting measure, b is the power set of x and mu is counting measure, and they are all infinite dimensional Banach spaces. LP 1 less than equal to p less than equal to infinity are examples of infinite dimensional Banach spaces. They are all Banach spaces of infinite dimension. So I have given another class of infinite dimensional Banach spaces. Each of them is infinite dimensional Banach space, and it has lot of interesting associated results in its own right. So in my previous lecture, somebody was asking, can you describe the continuous linear transformations on non-linear spaces? So today I am going to start that, and then towards the end I will give some of the results which I have research problems and some results. So one thing you see, this LP for 1 less than equal, if p is equal to 2, this L2, you get L2 with p 2 norm. This is a Hilbert space. Hilbert space. What is the inner product? So if you take x is equal to xn, suppose x is equal to xn, n is equal to 1 to infinity, y is equal to yn, again n is equal to infinity. So this inner product of xy, you'll get summation xn yn bar. This is a convergent series by Holder's inequality for p is equal to 2. This is a convergent series, and therefore it is a complex number. And you see, and the inner product induced by this is nothing but 2 norm. It is nothing but inner product of x with itself whole to the. So therefore this becomes Hilbert space for p is equal to 2. But if p is not equal, so now the question arises, given a norm-linear space or Banach space, when is a Hilbert space? The answer comes, see, if you have a non-linear, if you have an inner, if norm is coming from inner product, norm is induced by inner product, then it satisfies then it satisfies following identity, following parallel, what we call as following identity called parallelogram identity called parallelogram identity. And it is like this norm of, so if you have a parallelogram, suppose you have vectors like, you look at this plane, this is x and this is y, and look at this parallelogram, so this is parallel to y and this is x plus y, and what about this? And this will be x, this is x minus y, so this vector is x minus y. In any parallelogram in the plane, if you take length of x plus y square plus length of x minus y square, and this is 2 times length of x square plus length of y square. So this happens for all xy belonging to for all xy in the plane. So if this is what we call as parallelogram identity in a norm linear space. So if norm is coming from the inner product, suppose this norm is inner product of x with itself 1 by 2, then it is easy to see, then this norm satisfies following identity and you call it parallelogram. This satisfies this for all x and y belonging to x. So you have inner products, this norm linear space where norm is coming from inner product. It is induced by inner product in this particular way. Then it always satisfies this condition. Now, so if you have a Hilbert space, norm is coming from the inner product. So if P is not equal to 2, now you have this remark. If P is not equal to 2, suppose P is not equal to 2, then this LP is not a Hilbert space. How do we show this? So suppose you take x is equal to E1. E1 is 1 at the first place and elsewhere 0. Y is equal to E2. So this is 0, 1 and elsewhere all 0. Then if you look at this P norm of x plus y, what will be P norm of x plus y? So suppose your 1 is less than equal to P less than infinity, P norm of x plus y will be, so this is E1 plus E2 will be 1 comma 1 and elsewhere 0. So its P norm would be 1 to the power P plus 2 to the power P, 1 to the power P plus 1 to the power P whole to the power 1 by 2, 1 by P. So this is nothing but 2 to the power 1 by P. And P norm of x will be, what will be, if x is E1, what is the P norm of x? 1. Because there is only one component, 1 to the power P whole to the power 1 by P. So this is 1. And similarly this y is also, P norm of y is equal to 1. So if P is not equal to 2, if P is not equal to 2, so this x plus y. Similarly, and what is similarly, this is also equal to x minus y. X minus y P norm is also equal to root 2 to the power. So this is 2 to plus, so if you take square of this plus norm of x minus y P square, P norm, this is P norm square. So what will this will get 2 into 2 to the power 2 by P. Take square of this will become 2 to the power 2 by P. Plus similarly this 2 to the power 2 by, so plus 2 into 2 to the power. But if you take this 2 times norm of x square P norm plus norm of y square P norm square. So what do you get this? This is 2 into 1 plus 1 square करेंगे 1 का square 1. So this is 2 into 2 4. So this is not equal to this unless P is equal to, for P is equal to 2 this is equal. For P is not equal to 2 this is not equal. So therefore this LP space, so this implies LP 1 less than equal to P less than equal to infinity rather. Infinity also similarly can be shown. P not equal to 2 is not a Hilbert space. This is not a Hilbert space. And the other one also holds. So if a Banach space is a Hilbert space, if norm satisfies, if and only if norm satisfies parallelogram identity. If norm satisfies parallelogram identity, so a Banach space is a Hilbert space. This is a very famous result due to von Neumann. A Banach space, a theorem due to von Neumann. A Banach space x comma this is a Hilbert space. Is a Hilbert space if and only norm satisfies norm of x plus y square plus norm of x minus y square is 2 times norm of x square plus norm of y square for all xy belonging to x. And if this satisfies parallelogram identity. How do we get the inner product? Inner product is given by, inner product in this case, inner product in this case is given by norm as follows. So inner product of x comma y, this is 1 upon 4 norm of x plus y square plus minus, so it is, let me think about this, minus norm of x minus y square plus I times inner product of x plus iy square minus norm of x minus iy iota y whole square. So I can take here this curly bracket and this is here bracket and then this is iota y. So this and then you take this curly. This gives you the inner product if norm satisfies parallelogram identity. Again, this is a very simple result and I think you are familiar with this result, and some of you who are not familiar with this result, they would be familiar after some time. Okay, so this was all about Banach space, Hilbert space, and so on and so forth. So now I can divide continuous linear operator. Continuous linear transformations, or you also call them continuous bounded. These are equivalent bounded linear transformations. Let x and y be two norm linear spaces. Both of them either real norm linear spaces. See, these are over the field R or C. Both of them are real or both of them are complex norm linear spaces. So a linear transformation T from x to y is called a bounded linear transformation. It's called a bounded linear transformation. It is called a bounded linear transformation if there exists a positive real number m greater than 0 such that norm of Tx is less than equal to m times norm of x or all x belonging to x. If this condition is satisfied, then you call it bounded linear transformation from x to y. And there are examples of linear operators, linear transformations which are bounded, and there are one which are not bounded. So now remark which are bounded. Remark, if x is finite dimensional, then every linear transformation y, no, I am not putting any restriction on y. Suppose x is a finite dimensional non-linear space and therefore it is a Banach space, finite linear transformation, then every linear transformation from x to y is bounded. And the second is simple. If y is 0, suppose x may have infinite dimensions. If y is 0, then you get 0 linear transformation. Then again, every linear transformation from x to y is bounded, again bounded. But if x is not finite dimensional, and suppose y is not a zero nonlinear space, then you can find a linear transformation from x to y which is unbounded. You will have bounded linear transformation. Zero linear transformation is bounded, always bounded. But if x is infinite dimensional and if x is infinite dimensional and y is non-zero, then there are linear transformations always exists a linear transformation from x to y which is unbounded. So you have a whole lot of theory of unbounded linear operators, linear transformations. So I am not going into that because of the paucity of time. So now we have this proposition, let x and y be two non-linear spaces, and T from x to y be a linear transformation, transformation. Okay. Then the following statements are, they are equivalent, are equivalent. Number one, T is bounded. T is a bounded linear transformation from x to y. Number two, T is uniformly continuous. On x. And number three, T is continuous on x. Number three, T is continuous on x. And number four, T is continuous at the origin, at zero vector. So these four statements are equivalent, you see. So what this result says that, or in fact, T is continuous at some point x naught belonging to at least one point, at some point x naught. So this result says that if T is bounded, then it is uniformly continuous. It is continuous, and if you have a linear transformation between two Banaras non-linear spaces, and if it is continuous at some point, then it is continuous, it is bounded, and therefore it is uniformly continuous, and therefore it is continuous at every point. So you cannot have a bounded linear operator which is continuous at one point and discontinuous at other point. If it is bounded, it has to be uniformly continuous on x. So let us look at this. So one implies two. Proof. Look at the proof. They are very simple. So I am tempted to prove them. Suppose T is bounded. One implies two. T is bounded. So this means there exists an m greater than 0 such that norm of Tx is less than equal to m times norm of x for all x belonging to x. Now I want to show that T is uniformly continuous, that epsilon be greater than 0, and put delta is equal to epsilon. So this is also greater. Epsilon by m, because your m is positive. So delta, because this is positive, so it is positive number. Quotient of two positive numbers, real numbers, is a positive real number. Okay. So this is then for any x, y belonging to x with norm of x minus y less than delta, we have, what do we get? Norm of Tx minus Ty. T is linear, so I can write this as T of x minus y. And because T is bounded, this is less than equal to m times norm of x minus y. And this is less than m times norm of x minus 1, mind you, less than delta. So this is m delta, and delta is nothing but epsilon by m, so it is equal to epsilon. So thus for every epsilon you get a delta such that whenever you have x and y, any two vectors whose difference has norm less than delta, norm of Tx minus Ty is less than epsilon. And this implies T is uniformly continuous on the whole space X. Now if T is uniformly continuous, uniform continuity implies continuity, and it implies continuity 4. That's trivial. So if it is continuous on x, at every point it is continuous. Therefore it is continuous at any point, some point. Now the important point is 4 implies 1. How do you show that 4 implies 1? Suppose T is continuous. Let T be continuous at some point x naught belonging to some fixed point x naught. So this would imply, this implies T is continuous at it, this implies norm of, so for, suppose I take epsilon is equal to 1, it is greater than 0. Then for epsilon there exists a delta greater than, for epsilon there exists a greater, so Tx minus T of x naught, this is less than F1, epsilon is 1, whenever norm of x minus x naught is less than delta. Okay, so now what you do is that let x dash be 0 not equal to x dash be any vector in x, non-zero vector in x. Then if you look at this, then x is equal to, suppose I write x is equal to, so if x is non-zero, then norm of x dash will be greater than 0. Okay, because this is a non-zero arbitrary vector, arbitrary non. Then now I write this x is equal to, okay, so what I can write is so what should I do? So what I do is the thing, nothing but, so this is nothing but x dash divided by norm of x dash. So this is a greater than 0 plus, and this is delta by 2. You take multiply by this scalar. This is a scalar, so I can write like this. Let me see. So delta by 2 times norm of x dash into x plus x naught. So this is x dash. So you have a non-zero vector and this is a scalar, positive real number. So this scalar multiplied, this is again a vector in x plus x naught. So you are translating this vector by x naught. This also belongs to x. And this vector, then what is norm of x minus x naught? So what will be this? X naught gets cancelled. So this will become delta by 2 times norm of x dash into x dash. And what will be this? This is delta by 2 times norm of x dash into norm of x dash. And this is delta by 2. Delta by 2 is less than delta. So x minus x naught is less than delta. And that would imply by this first condition, number 1, this, so from equation number 1, norm of t is continuous, Tx minus Tx naught is less than epsilon is equal to 1. Okay, because norm of x minus x naught is less than delta, because of the point of continuity of this t at x naught, you get this. So so this implies, now you put the value of x, this is t of delta by 2 times norm of x dash into x dash minus plus x naught minus t of x naught. And this is less than 1. And so you see, t is linear, so this will become, so this implies norm of delta by 2 times norm of x dash, t of x dash plus t of x naught minus t of x naught. T of x naught gets cancelled and this is less than 1. So this would imply, so this is a scalar and this is non-negative scalar, this modulus is itself delta by 2 times norm of x dash into t of x dash norm, this norm of this is less than 1. And that implies norm of t x dash is less than equal to, so 2 upon delta into norm of x dash, and this is for all x belonging to capital X minus 0 vector. So this is x dash for all x dash belonging to this. But if you put x dash is equal to 0, t of 0 is 0, so this becomes 0. 0 vector as norm 0. So this implies norm of tx is less than equal to, suppose I write m times norm of x for all x belonging to x, where your m is 2 by delta, which is greater than 0. So you got a positive real number such that norm of Tx is less than equal to m times norm of x for all x. And this implies that T is bounded. And thus 4 implies 1. So these 4 statements are equivalent. So if T is a linear transformation between two non-linear spaces, then you have these 4. These 4 conditions are equivalent. So given two non-linear spaces, so you look at this. So let x and y be non-linear spaces. Linear spaces, right? Let bxy the set of all bounded or continuous. Boundedness implies bounded or continuous linear transformations from x to y. And this is a subset of Lxy. This is nothing but space of all linear transformation from x to y. So this is a vector space. You know, if you have two vector spaces, look at all linear transformation from between those vector spaces. It is a vector space. And when x and y are both finite dimensional, this is finite dimensional vector space. And this is a subset of this. Now, I can show that this, if T1 and T2 are linear transformation, so now this is a simple exercise. This Bxy is a subspace of Lxy. This is a subspace of this vector space. Now the question is, can you define a norm? Can you make it a norm-linear space? The answer is yes. So now for T belongs to Bxy, you write norm of T is nothing but supremum of norm of Tx, where x varies over x, where x varies over x belongs to x, norm of x is equal to less than equal to 1. Then this Bxy with this norm defined like this, this becomes a non-linear space. Again a non-linear space. Now the question is, when is it a Banach space? The answer is y is a Banach space. If y is a Banach space, then Bxy is a Banach space. Now, if suppose your y is 0, suppose x is 0, then again it will become 0. So this can be 0. When x is 0, then Bxy is 0. Bxy, this is also 0 space. This is also a Banach space. But when suppose x is not 0, then Bxy is a Banach space if and only if y is a Banach space. The converse also holds. If x is non-zero non-linear space, then Bxy is a Banach space if and only if, this is if and only if y is a Banach space. So if Bxy is a Banach space, y has to be Banach space. And if y is a Banach space, this is always a Banach space, you see. So a lot of Banach space theory has developed along these lines. So there are unsolved problems in Banach space theory where you can work. For example, if you have suppose you have two closed subspaces of Banach space. So M1 and suppose you are unsolved problem. This is unsolved problem. Let x be a Banach space, and M be a closed subspace. closed subspace of X. Then you have this problem. So this is called problem complemented subspace problem. Complemented subspace problem. M be a closed subspace. Then M is called a complemented subspace. Then M is called a complemented subspace. Complemented subspace of X if there exists another, if there exists a closed subspace, another closed subspace n such that M plus n direct sum is all of X. So this M is called a complemented subspace. A closed subspace of X is called a complemented subspace if there exists another subspace n. There exists a closed subspace n of X of course, such that M direction is equal to all of X. In general, this problem has the solution of this problem has been worked out in many ways, and one of the famous mathematician got Fields Medal while trying to solve this problem. But the complete solution of this problem is still an unsolved problem. And a particular case of this problem is a particular case of this problem, a sub-problem of this problem. This problem is following problem. Now one more. Now at this stage I want to make an observation. Suppose X is a Hilbert space, and M is a closed subspace of this X, where H is a Hilbert space. Then you know that, then you define orthogonal complement of M. What is this? Orthogonal complement of M is nothing but all y belonging to X, Hilbert space X, such that inner product xy is equal to 0 for all X belonging to M. So this is called the orthogonal complement of M. And the result says that this is a closed subspace. Because of this inner product is continuous. Using this continuity of inner product, one can show that M perp is a closed subspace of this Hilbert space X. If X is, and one can show that this direct sum of, this is very simple, M direct sum M perp is all of it. So this problem, complemented subspace problem, is very easy, has a simple answer in the setting of Hilbert space. But in general Banach space setting, it does not have a complete answer. So this remains it. So when you go from Banach space to Hilbert space to Banach space, the problem becomes much more complicated. So setting of Hilbert space is very simple, whereas in the Banach space setting, it becomes much more complicated. Therefore, whereas here it has simply answer M perp. So n is equal to, you take n is equal to M perp. Then M direction n is equal to all of X. So this problem. But in general Banach space setting, you do not have answer of this way. And it has partial answers given by famous mathematician, one of the famous Israeli mathematicians who got Fields Medal in mathematics. Now a sub-problem of this problem. We worked on a sub-problem of this problem. Suppose you have a so sub-problem of this problem is, suppose X is a Banach space, so X is a Banach space, and M and N are closed subspaces of X. Now suppose this M intersection N is 0, then so you can talk, so when is direct sum of M plus N is a closed subspace. This is a closed, this is a closed subspace of X. So suppose M and M intersection N is, so in general, So if you don't restrict this thing, suppose M and N are two closed subspaces and take their sum. When is sum of two closed subspaces of a Banach space closed subspace? This again remains a so in general, if you look at Hilbert space problem book by Almost, so sum of two closed subspaces need not be a closed subspace, even in Hilbert space. Now the question is, given any two closed subspaces, when is there some closed subspace? So this again, this problem remains unsolved problem. It is still an unsolved problem. So if I mean, when is this closed subspace? These are at least two problems that I have given, which look very simple, understandable. Closed subspace of a Banach space is a Banach space. So these are closed subspaces, means this is a smaller Banach space sitting inside X. So okay. So I worked in this complemented. One of my student, PhD student, did PhD in this problem, complemented subspace problem. And okay. So another problem. So this was one unsolved problem called complemented subspace problem. A sub-problem of this problem is coming from this problem is, given M and N are two closed subspaces, when is it the sum of two closed subspaces of a Banach space, again a Banach space. This remains an unsolved problem. In general, this is not true, as I told you. Now, when is this sum of two closed subspaces a closed subspace? The answer is still eluding all of us, mathematical community. So therefore, you can work with this problem. One is complemented subspace problem. The other is a sub-problem of a more general problem, or you can say it is sub-problem in some sense, that if M and N are two closed subspaces, when is the sum of their sum a closed subspace? And in general, Halmos showed in his problem book that sum of two closed subspaces need not be a closed subspace. Now, what additional condition that you can put that so that on M and N, so that it becomes a closed subspace? In fact, direct sum of two closed subspaces need not be a closed subspace. So what additional condition on the Banach space setting on the given closed subspaces that you can put so that their sum become a closed subspace? So this is simple looks very simple, understandable, but its answer still eludes all of us. So this could be another problem. Now the third problem will come. So all these problems in all these problems I have obtained some new results, but however I still do not find a complete solution, and I recommend that some of you to work out in this area. Okay. So now, another area where I worked is what we call as operator theory, called composition operators. Composition operators. This is my area of specialization, composition operators. Composition operators. For that, you have to have some understanding. Let X be mu be a sigma finite measure space. Be a sigma finite measure space. Measure space. So by sigma finite measure space, you mean that this mu is sigma finite. Meaning thereby, this X can be written as countable union of measurable sets of finite measure E. That is, this X can be written as measurable union of N. So this mu is sigma finite. Mu is sigma finite if X can be written as this union of N is equal to 1 to infinity, where each An belongs to this sigma algebra, and mu of An is less than finite for each N. Then this measure mu is called sigma finite. So given a sigma finite measure space, look at the LP space. I defined LP space of X, B, mu. Now, this is a Banach space. This is a Banach space, and for P is equal to 2 Banach space, and for P is equal to 2, this becomes a Hilbert space. Therefore, you can talk of bounded linear operators from let phi from X to X be a measurable transformation. Suppose it is a measurable transformation. Measurable transformation. What is a measurable transformation? By a measurable transformation, we mean that if you take any measurable set So if measurable transformation means for each measurable set, for each B belonging to this phi inverse of B is also, this also belongs to this. Inverse of a measurable set is, of each measurable set is measurable. Then this phi is called a measurable transformation. So this measurable transformation, suppose this phi is a measurable transformation such that mu phi inverse. Mu phi inverse is again defined on the sigma algebra to R plus as mu phi inverse of E is equal to mu of phi inverse of E. So if E is any measurable set, phi inverse, because phi is a measurable transformation, so this phi inverse E is also a measurable transformation. So therefore it makes sense. And this mu phi inverse is a measure. Mu phi inverse, if phi is any measurable transformation, set is this, then this mu phi inverse is again a, mu phi inverse is a measure, is again a measure on X. This is a measure on X. Now we put some additional condition. Suppose this mu phi inverse is absolutely continuous with respect to mu. What does this mean? This means that if E is any measurable set, E is measurable, E belongs to sigma algebra such that mu of E is 0 implies mu of phi inverse of E, this is also 0. So then you call this to be absolutely continuous with respect to mu. So suppose you have a measurable transformation phi from X to X, which that means measurable means this, and then such that this mu phi inverse is absolutely continuous with respect to mu, then it defines a linear transformation. Now if phi has these two conditions, first condition is it must be a measurable transformation. Second is this measure induced by phi, namely mu phi inverse, is absolutely continuous with respect to mu. Then I can define a linear transformation from, then if these two conditions are satisfied, then I can define C phi from LP of mu to LP of capital LP of mu as C phi of f is equal to f composition f. So what it does is, you take any function here, it composes here. So this also belongs to LP. So this C phi defines a linear transformation on LP of mu, from LP of mu to LP of mu, and this is called a composition transformation. So this C phi is called a composition transformation induced by phi, because it involves composition, you see. So this is called composition transformation induced by phi. And if C phi is a bounded linear operator, bounded linear transformation on LP of mu, then C phi is called a composition. Then C phi is called composition operator. Composition operator on LP of mu. So this is called a composition operator LP of mu. So now the question is, in this setting there are various questions. So now the first question is, when is C phi bounded linear operator? When is the question number one? Question one, when is C phi bounded? So this answer has been given by some famous mathematician. So this C phi is bounded if and only if you take the Redan-Nikodym derivative of mu phi inverse by d mu. This must lie in L infinity of mu. So this C phi, this composition transformation, from LP of mu to LP of mu is a bounded linear operator. This is a bounded linear transformation. If you look at if and only, because this mu phi inverse is, I demand that mu phi inverse is absolutely continuous with respect to mu. So therefore this makes sense. This is Redan-Nikodym derivative. radon nicotine derivative of mu phi inverse with respect to mu. So this makes sense. So this must be in L infinity of mu. The C phi is a bounded linear operator if and only if the radon this function must be essentially bounded. Then only then this C phi from LP to LP is a composition operator. It is a bounded linear operator. Now once you get the bounded linear operator, there are various operator theory. Now what is the spectrum of C phi? Question: find spectrum of C phi is nothing but all lambda belonging to C, such that C phi minus lambda I is not invertible. This is not invertible. So the question of finding spectrum is one of the challenging unsolved problem in generalized setting. In special cases, problem of research in operator theory. There is another problem in operator theory, unsolved problem. In all that unsolved problem is that is if you have a bounded linear operator on Hilbert space, which is non-trivial bound zero, it is not zero on an inseparable Hilbert space, does it has a non-trivial invariant subspace, closed invariant subspace. In the Banach space setting, this has answer, but in Hilbert space setting, this does not have answer so far. Does every non-trivial bounded linear operator on a separable Hilbert space has a non-trivial invariant subspace? This is a classical famous invariant subspace problem, which has not been answered so far. It still remains a conjecture. Now, this problem of invariant subspace has been translated in terms of problem for invariant subspace problem for composition operators. So this problem C phi. So this has been translated into a simple problem for composition operators. So you look at H2 of D, H2 a Hardy space. D is the unit disk. All Z such that mod Z is less than complex plane. So this is in the open unit disk in the complex plane, and you take this H in the H2 of D. H2 of D is nothing but all analytic functions from D to C, such that if you look at this, its series, it's a power series. So Fz can be, because this is analytic, so you can write this an z to the power n. And this belongs to H2 of D, such that summation if mod of an square, n is equal to 1 to n. So this is a Hilbert space, you see. Hilbert space with two norms. You have two norms here. So this is a Hilbert space. Now this you can define composition of operator C phi on H2 of D to H2 of D. Similarly, as we have defined for this arbitrary measure space, if phi is analytic function from D to D, it induces analytic. Then it induces a bounded linear operators from H2 of this Hilbert space to itself, and its norm of C phi is less than or equal to 1 plus mod of phi 0 divided by 1 minus mod of phi 0 and this whole to the power 1 by 2. It is a bounded linear always bounded linear operator. And therefore, now the question is, what are all its invariant subspaces? Because so this again does not have an answer. So this, and moreover, any bounded linear operator on so the general problem is finding bounded that is invariant subspace for a bounded linear operator. So this problem can be put in the setting of composition operators. The C phi, this every non-trivial bounded linear operator on a Hilbert space, on a separable Hilbert space, Hilbert space has a non-trivial solution, that is, it has a non-trivial this non-trivial invariant subspace. Non-trivial solution is non-trivial invariant subspace. If and only if this C phi from S2 to S2 of D to S2 of D has a non-trivial. So for this composition operator, has a non-trivial invariant subspace. Invariant subspace for, so it has if and only of, and also all minimal invariant subspaces of C phi are one-dimensional. So if every composition operator from S2 to S2D to S2D has all minimal invariant subspaces of dimension 1 only, then this has an affirmative answer. Otherwise not, if and only. So that means the invariant subspace problem in a generalized Hilbert space can be translated into problems of composition operators in the Hardy space, S2 of D. So this is a remarkable improvement, result relating classical invariant subspace problem to composition operator, finding invariant subspaces of composition operator. So I forgot this define. So a closed subspace, and suppose you have a Hilbert space and T is bounded linear operator from H to H, and M is this is bounded linear operator. A closed subspace M is called invariant. This is called invariant under T if T of M is nothing but all Tx where x belongs to M. This is always contained in. Then you call M to be invariant under T. So this is a simple looking problem in the operator theory, but it has not been tractable so far. It has not been solved so far. And the remarkable result on composition operators is that this problem can be translated in terms of transferred in for composition operators. That you look at minimal invariant subspaces of certain composition operators, and if they are all finite dimensional, then this problem has affirmative answer. Otherwise, it does not have affirmative answer. So that's remarkable, and there are many facets of composition operators which are still to be explored, and there are many monographs on composition operators. One is by Shapiro and Sandberg. So Shapiro, this H is Shapiro, this is composition operators on spaces of analytic functions. These analytic spaces of analytic functions are more interesting because the theory of complex analysis and operator theory both merge together. They meet together. In the first lecture, I said that whenever different ideas of mathematics converge together, that gives rise to a new and beautiful mathematics. So these spaces of analytic functions is a meeting point of functional analysis and classical analysis. So this is very good monograph. So this is monograph. So it has come from monograph. And there are many monographs. If you look at Google search, you will find many monographs. And they illuminate the idea of studying composition operators. It represents diverse class of examples in operator theory. And it illuminates whole of operator theory. Because the complicated problem of operator theory can be put in the setting of composition operators. And composition operators are easy to see. क्या? अच्छा with this with my this lecture. I think this is the final lecture as of now, because from tomorrow onwards there is holiday, that Deepavali holiday. I wish all of you a happy Deepavali. And if you have any questions, then you can email me. You can communicate through social media, various ways, means of social media, WhatsApp, and I will be ready to answer each and every question subject to my competence. So I feel humble here with the kind invitation that Professor Garology gave me, and gave me this opportunity to come over this beautiful campus. And my mission now is, whatever knowledge I have been imparted through different means, I would like to impart it to younger generation, so that you further, you reach newer heights, you become higher, you become a greater mathematician, and many of the students from these regions must rise to international level, especially as far as mathematics is concerned. This is our lifelong aspiration. So thank you all for your patient hearing.